All right, so in this module, we're going to talk about what's called Pauline's rules. These allow us to predict the structure of ionically bonded materials. So let's go ahead and get to those rules. All right, so here's a summary, and then we'll talk more in detail about each one of them. But the idea is this is an attempt to try to predict these structures. And again, it's for ionically bonded compounds, and that's where the covalency factor kind of comes in. So anytime we have covalency, it kind of messes up these predictions, but it tries to predict the structure based on a balance of the forces. So first one is coordinated polyhedron of anions are formed around each cation. So basically, anions are formed around the cations. In the second, we have to, for a stable structure, what's called the total strength of the bonds that reach each anion in a coordinated polyhedron should be equal to the charge of the anion. All right, so this is basically charge balance, so to speak. And then third, the polyhedra in the structure tend not to share edges or faces. So corners are the most stable sharing feature. And then four, crystals containing different cations. So this is in a case where we have more than a binary compound. So this only really applies for that. So if it contains different cations of high valence and small coordination number tend to not share polyhedron elements with each other. And then the last one, again, this applies to more complex structures. The number of essentially different kinds of constituents in the crystal tends to be the smallest it can be. All right, so let's start and kind of go through in order to look at what these are. So the first one, so this predicts the cation, what we call the cation coordination, because the anions are surrounding the cation. And we get these from simple geometry. And so some of the kind of proofs are kind of shown here for you. So this configuration where a cation is surrounded by 8, right? And you basically this is showing you the calculation for the critical cation to anion. It says mx, but that's cation and anion, and so it shows you the calculation for that. Same thing here. This is for coordination 6, and it shows you through how one way in which you can get that critical value for the coordination. So we're looking for the critical values of that ratio, right? Because we saw that ratio was what we're going to look at. And then this is for coordination number 4. So these kind of walk us through how those calculations are done to find the critical size. So again, keep in mind, if we go back to the previous module, this was the critical size. So basically when everything is just touching, so we know that there's contact along this diagonal and then along this line as well. And so we can use geometry like we're showing here to calculate what the ratio of the radii would be. And so that's what it's showing here. And so the end result here, so this is taken from the MSE 201 textbook Callister, and it basically shows you the critical values for each coordination. So we start with 2, and if the cation to anion ratio is above 0.155, then we get a coordination number of 2. Below 0.155, then we get a coordination number of 2. And so that is linear. That's what you see here. Number 3 is just above that critical value, and then just below this 0.225, which happens to be the critical value for the next. And so this one is tetragonal planar. And so these first two aren't common in the structures that we'll look at, but 4, 6, and 8, which are tetrahedral, octahedral, and cubic respectively, are important. And you see that the ratio range, so the critical low value, 0.225, up to 0.414, which is the critical for the next and then the next, right? And so if those numbers look familiar, it's because some of them were on the previous page. Excuse me. So these are the ranges. So basically, by calculating the ratio between a cation and anion, we can start to predict what the cation coordination will be based on these geometric size considerations, right? So that's what the first rule is about. The second rule is, in essence, the opposite, predicting the anion coordination. So we know the cation coordination if we apply the first rule. So now the second rule, and we try to predict the anion coordination of the structure. And we do that with a thing called bond strength, and that's what S is. So the bond strength is equal to the charge of the metal. So Z is charge, M is for metal or cation, and then the coordination number, this is also for the metal. So we've just calculated this with Pauline's first rule. We know the charge if we know the material that we have, and so we can calculate the bond strength. So let's go through a rule, an example of this using the second rule here. So let's say we have Al2O3. So let's say we already calculated the coordination number of aluminum to be 6. And from the stoichiometry here, oxygen always has a 2- charge, so that would give aluminum a 3+. And so we've got the charge of aluminum, so that's up here, coordination down here, and so we can calculate the bond strength to be plus 3/6, which is the same, obviously, as plus 1/2. And so in doing that, this is the bond strength, and so this is then related to the charge of the anion. So essentially oxygen, right? And so we can get that by how many of these bond strength aluminums have to be around the charge of one oxygen. And so 4 times 1/2 is equal to 2, which is the charge of the oxygen. So we have to basically balance it. And so effectively, since 4 aluminums surround it, that gives us the anion coordination. So if this seems a little kind of unorganized way of doing it, what you can also do is the bond strength up here, where you have the charge of the metal and the the coordination of the metal or cation. You can also restate this expression because the bond strength for the anion is equal to the bond strength of cation. So you can also set this equal to Z of the anion over coordination number of the anion and rearrange that and solve it in the same way. So again, as an example, you can try this one as well. So titanium dioxide, we're giving you the cation, the coordination number for that, and then the charge, because again, we know oxygen, and so calculate the bond strength and see if you can get the coordination number for that one. So I'll put this one in the quiz. So if you want to sort of set this one as a quiz question, and go ahead and pause the video, see if you can determine the bond strength, but also the coordination number of the anion, just like we did with this example. So pause the video, come back, and we'll discuss. So let's see if we can calculate the bond strength of TiO2 using Pauline's second rule, and then the anion coordination like we did in the previous example. So our bond strength equation is this, and I'm going to go ahead and choose maybe more consistent subscripts. So C and C, both of these are for cation. Again, some of the slides are saying M. That's because different resources call it metal, some of them call it cation. So we're just going to use cation in this example here. So this is the bond strength equation. The charge of the cation, which is the metal, is titanium, and so we know that the charge is +4. And then the coordination number, which we're given in this case, but if we weren't, we could apply the first Pauline's rule to predict that. And so we get 6, right? So it's not tricky math-wise or anything like that, but just a quick expression to give us the bond strength. So that gives us 2/3, right? So if we reduce it. And so, like I was saying before, we can also rewrite this bond strength because the bond strength is the same for the cation and the anion. So we can rewrite this as the anion over the coordination number of the anion. So we're after the coordination number of the anion. Sorry about that. And so we can rearrange this expression to solve for it. My dog senses danger outside. So if we rearrange it, we get this, right? So we know the charge of the anion from up here. And so we'll use the charge here. And so one thing I'll mention, the bond strength, they are equal, but they are also opposite. So I'll also put a negative down here, right? Because one has to do with negatives and positives. So they are equal and opposite. So if I go ahead and put that in, my bond strength was plus 2/3. And so now it's going to be minus 2/3, right? And so if I do that, that's going to give me what? 6 divided by 2. So this is 3. So I've calculated my bond strength as this from the first part. And then my coordination number of the anion is 3. So if I know this, then the coordination number of the cation and anion, this really tells me most of what I need to know about the structure. And so later on, we're going to see how to piece these details together to give us what this structure is. All right, so we've looked at the first 2 rules, so let's look at the third now. And this one has to do with the polyhedra that are formed in the structure. And so if we look at each of one of these, in the center of these shapes is a cation, or it can be an anion. It doesn't matter in some of these cases. But the shapes, the polyhedra that are described here, are the coordinating species. So the things surrounding that one central ion in the middle. And so these are obviously the faces and everything are in essence non-existent, right? It's just a way of describing the shape of the things surrounding the central anion or cation. So but we are looking at these shapes now, and we're looking at how they're shared. And so this is an example of vertex or corner. So the corners of the polyhedra are shared, or vertex. Here, if you look at this rock salt structure, the edge or line between 2 polyhedra is shared. And then over here, you see some aspects where this polyhedra here and this one share an entire face. So the third rule tells us that the face sharing is the least favorable, followed by this, followed by vertex, which is obviously the most favorable of these. And the reason this is because if we look at face and edge sharing, it decreases stability because the cations, which are in the center of the polyhedra, become closer and closer. So if we just kind of take one polyhedra, for example, and we just think of this one shape, the closest we can get those cations together is if we share faces. And then the farthest apart they would be is if they shared edges. So basically this is trying to minimize the cation repulsion by having them further and further apart. And so that's just one example. So it becomes, the cations become too close together. And just a kind of a quick note here that this effect is high when we're dealing with high valence and small coordination number cations. All right, so let's look at the fourth and fifth rule now. So the fourth like I mentioned, this is for when we have different cations. And so this is going to be for more complex multi-cation structures. So not the binary ones that you're probably most familiar with. But the idea here is that those different cations tend to not share polyhedra elements. So here we have one cation, and then in this polyhedra we have a different, and they're not sharing the same element. So they have different polyhedra is the idea with this. So this is the perovskite structure. And so we have octahedral and for this one, and then a different polyhedra for the other one. So you can kind of think of this as an extension in the third rule, but doing it we're trying to keep the cations as far apart as possible, but we're talking about dissimilar charges. So if you're only dealing with a binary structure, we don't even have to consider the fourth rule in the fifth rule. So this is only for those more complex structures. And the fifth one is saying, the fifth rule is saying that like ions tend to exist in similar environments. So an example here, so this is garnet, so you can see multiple cations. And so if we look at oxygen in this case, we see that oxygen will tend to want to be in a similar environment, and that's to have, bonded to two calciums, aluminum, and a silicon in this way. And so you see this kind of very complicated structure, but that's showing you that like ions, like the oxygen, will tend to want to be in similar environments. However, if we have differently charged ions, then they will tend to have different coordinations. But oxygen, however, tends to have very consistent surroundings.